Okay, so we have a problem here that's very similar to the last one that we just did, except that it's at an angle. And we got a 20-degree incline in here this way. Now that changes some things. I mean, we still have the same kind of initial conditions. It's sliding to the right. Okay, so we've got some velocity headed this way, just like that. And I'm still gonna come in here and say that we'll go ahead and call this. We're gonna expect the acceleration to be this way. Okay, and so if we put our forces on here, then we've got the weight, which is M2G of that guy, and we're gonna have a perpendicular component, parallel component of M1. And here then we've got the perpendicular component of N1, and of course we have the normal force, just like that. All right, now I'm going to work this as one unified system, so I'm not going to worry about the tension. Okay, we could set it up that way if we wanted to. So let me unwrap this thing and kind of show you what it looks like if we think about it as a unified system. Then we have this, okay. And here's our M2G. And we have friction. We have the parallel component of the first mass. We have the perpendicular component of weight of the first mass. And we've got the normal force. Okay. So now the tension doesn't really matter. And again, we're going to say acceleration's this way. Okay, so here we go. Let's start off with looking at our system, looking at what's happening with the y components of force, MAY, just like that. So I'm going to have my normal force up and my perpendicular component of weight down. Okay, and there's no acceleration in that direction, so we put equals 0. So then the normal force becomes our perpendicular component, like so. And that becomes M1G cosine theta. Okay, and again, we've talked about this before. You really probably should just memorize parallel and perpendicular components, okay, when we're dealing with the ramp, because they come up a lot. Okay, you don't want to have to stop every time and be like, now which one is which is which? Just kind of stick that one in there for good measure. Okay, now what this does for us too is it allows us to say that our friction, once we get to that, is mu times the normal force. So we're looking at mu M1G cosine theta. Okay, so that's our frictional force. Now let's get to what's happening horizontally. Okay, Fx is max. There we go. So now we're going to have minus that parallel component minus the friction plus M2G, and that's going to be the total mass M1 plus M2 times the acceleration. Okay, and again, we'll skip the AX because we already know it's in the X direction. Okay, and so let's expand a little bit. The parallel component of that weight for M1 is mg sine theta. Then the friction, we put that in minus M1G cosine theta plus M2G, and that's M1 plus M2 onto A. Okay. All right, now I'm going to skip several lines of algebra. You should do it yourself, okay, so that you could be confident in how it happens, all right, in case you have to do something like this on the test especially. But what we're going to get is that A is G onto make sure I need to write this down correctly. M2 minus M1. And then we're going to have sine theta plus mu cosine theta. And all that's over M1 plus M2. Okay, so let's put in some numbers here. We've got 9.81 meters per second squared. Gonna get a little messy here. M2 is 1.5 kilograms and minus 5 kilograms onto sine 20 plus. All right, we can move this around. Okay, got a little technical problem there. Okay, that's gonna help. Oops. Okay, plus mu cosine 20. All that's going to be over 1.5 kilograms plus 5 kilograms. Okay, and so let's look at our units. All right, I've got kilograms in the top. I've got kilograms in my denominator. Those are going to cancel, and I'm left with meters per second squared. So that works out kind of cool. All right, and let's get the answer. A turns out to be negative 1.74 meters per second squared. All right, so what does that mean? Well, we defined positive A for the system to be going like this, okay? And it's moving that way. What we find out, though, is that it's not speeding up. It's actually slowing down, okay? It's slowing down as it goes up the ramp, okay? I mean, in the last one, our acceleration was really tiny. It was less than 1. And so in that case, the 1.5 kilogram mass was sort of barely able to make it accelerate. Okay, in this case, though, with the incline, it just can't do it. So if we wanted M1 to have a positive acceleration to move faster and faster and faster, we'd have to add a bigger mass for M2. Okay, so there you go.